remember to start the recording this time. Here we are. This is our second day of section 7.1, which is integration. So last time, at the end of the lecture, we proved that if you are Riemann integrable, then your integral is unique. Okay? And by the way, we define the integral, which you can remember how we've written here. That's a good way to remember it. I'm just going to point out we haven't technically defined a limit over tagged partitions or something. So it's not technically a limit, but it is morally a limit. We're letting the norm of the tagged partition go to 0, and we're asking what happens to this sum. Okay. Oh, and I guess I should have pointed out last lecture, but I'll point it out today, that this symbol in the integral looks like an S for a reason. Okay, so this S on the right-hand side here literally is an S, and it stands for summation, or sum. And the integral on the left is supposed to remind you of a sum as well, and that's why it looks like an S. Okay, so let's start out today with a definition. Well, I guess it's really a symbolism. We're going to use this symbol to denote the set of all Riemann integrable functions on the domain A to B. So from the closed interval AB to the reals. Okay, I put Riemann in parentheses because for the purposes of this class, integrable is always going to mean Riemann integrable. But more broadly, there are actually quite a few different definitions of integrable. But we're only going to have this one. Okay, so that's our one definition for today. Now we have 3 theorems. So let's get started. Actually, I think we have 3 results. Only 2 of them are called, should be called theorems. Okay, so the first one tells us about the linearity properties of the integral. Okay, so if you've taken linear algebra, what I mean is that the integral is a linear operator, or a linear map. Okay, so it satisfies the 2 linearity things you would want from a linear map. If we multiply a function by a constant, or I'm calling it a scalar here, since we're talking about linear maps, the function will still be integrable, and of course we know the integral. Right? Constants come out. And the second one is that if you add 2 functions, then the sum is still integrable. And again, we know the integral is just the sum of the 2 integrals. Okay, so these are 2 facts that are hopefully obvious. Well, they're at least well known to you. They probably aren't obvious in the sense of, you probably don't know the proof by heart. So our goal today is to prove them. Now,
Professor,
Yeah.
in the conditions in the theorem, should f and g... Oh, no, I'm sorry. In number 1, not in the conditions. Should CF be in, like, the like, swirly cursive R, or, like, the real numbers type R?
Yeah, what am I doing? Thank you. That is a bizarre error. For me to make. Thank you. So yes, CF is integrable, and and F plus G is also integrable. Okay. Now, the proofs.
I have a quick question.
Go ahead, Daniel.
I'm looking back through what we defined in the integral, and I'm just wondering, like if we're just borrowing the dx convention here, like I don't really see, and I'm looking through my notes, I don't see where we kind of said what what dx is, and all that. You know, maybe it's not very important right now, but I'm just
okay. So, I guess I should have looked at how we did it back on Monday. Did we not use the dx on Monday?
I'm looking through my notes and I don't even see the integral sign.
Oh.
Yeah.
Well, okay. So I'm sorry. I guess we skipped over that. Well, okay. Then at the end of the last lecture, we proved that if you're Riemann integrable, you have a unique integral.
Right.
And we are going to denote that unique integral by this symbolism right there.
Okay. And then dx is just to let us know that we're doing the partitions of x.
So dx is, yeah, so from our perspective, dx is just telling us that that we're integrating with respect to x. It's a little bit, what's the word I want to use, like vestigial? Vestigial, that's what I want to use, vestigial. In the sense that, like, you know, when Newton and Leibniz did this, dx actually meant an infinitesimally small distance of x. And so you were actually summing that function where, you know, the function times the little tiny infinitesimal value of x. dx doesn't mean that anymore. Because, you know, we've done away with infinitesimals. So
Okay.
It's vestigial, yes.
So it's just a little reminder.
It's a reminder that we're doing it with respect to x.
Okay.
Yeah. Okay. So both proofs are really similar. So we're going to do the harder one, which is 2. So proof of 2. We're going to let an epsilon be given. Okay, what do we need to show? We need to show there exists a delta, so that no matter which tagged partition we take, as long as the norm of that tagged partition is less than delta, then S of F plus G with respect to that tagged partition is within epsilon of the answer it's supposed to be. And that's what it's supposed to be. That's what we're claiming it is. Okay? This thing on the left, that's just how we're denoting the integral of F plus G. Okay, and if we can show that the answer is right, then it will follow immediately that, of course, it was integrable, because that's the definition of integrable. Okay, so what do we know? We know F and G are integrable. So we're going to take their deltas. So let's start with F. It has a delta F. Delta sub F is how I'll denote it, such that for any tagged partition P dot with norm less than delta sub F, what do we have? We have that this sum of F with respect to the partition P, the tagged partition P dot actually, is within epsilon, in fact I'm going to go epsilon over 2 of the integral. Okay. Because we were given that F is integrable. So that means that these sums, these S of FP dots, are approaching some number which we've defined to be the integral of F from A to B. Okay? So we can get within epsilon over 2. So delta sub F is how small we need the partition to be, how fine we need the partition to be to get that close. Let's do the same thing with G. So there is also a delta G such that for any tagged partition P dot with norm less than delta sub G, we have the same condition, but with G okay. Now, last time I believe we would have written this delta sub F of epsilon over 2. Okay. You can do that if you want, just to remind yourself that that's the delta for epsilon over 2. Or you can not do it, like we've done our limit proofs. We never wrote a delta of epsilon there. So it's up to you. Okay, so delta sub F tells us how fine we need the partitions to be to get close to the integral of F, and delta sub G tells us how fine we need the partitions to be to get close to the integral of G. We want to do the integral of F plus G, so we're going to want our partitions to be both delta sub F fine and delta sub G fine. So we do a classic move. We just set delta to be the minimum. Okay. Now, for every tagged partition P dot, I'm not even saying anything about its norm. If we look at the sum of F plus G with respect to that tagged partition, Benjamin's right, the triangle inequality is coming, but I've delayed it for this line right here. So you think about what is this? This is the sum from, depending on what P dot is, but we're doing like F plus G, we're evaluating at TI, those are the tags, and then we're multiplying by our delta xi's, okay? And that's just a finite sum of things. And so we see that we can actually split it into two sums, and then you see that you can just write this as SFP dot plus SGP dot. Okay? So that's just using really basic things about sums of finite lists of numbers. That's true. Now we see that for every tag partition, P dot that has norm less than delta, well, what do we have? We're going to look at the difference between the sum of f plus g with respect to P dot and what we would like the integral to be. What we would like the integral to be is the sum of the two integrals. So I'm going to put over here what we would like it to be. That is the quantity we are interested in evaluating, and that's the quantity we would like to make less than epsilon. Okay. Now, we just said in the line above that we can split that S. So we can split the S and then I'm going to distribute that negative across. I'm going to put the F integral over there. And then I'm going to have the G's over here. Okay. And now we get the triangle inequality. Okay, so absolute value of the sum is at most the sum of the absolute values. I can drop those parentheses now. Okay. Now, P dot has norm less than delta. Delta was the minimum of delta F and delta G. So the difference between S of F P dot and the integral of F is less than epsilon over 2. And the distance over here is less than epsilon over 2. So the whole thing is less than epsilon. And that is what we need to show that the integral really does exist and is what we claimed it is. Let me zoom out for a second so we can see the whole proof. Oh, or is it going to get too small if we do that? There we are. There's the whole theorem with the proof. Are there any questions before we move on to our second result? I guess I should point out that obviously we could extend this additivity to any finite number of functions. So if we're integrating, f1 plus f2 plus f3 and so on, that's the sum of the integrals of those functions, as long as there's only a finite number of them. You can't do it. You can't extend it to an infinite number of functions.
So the trick for this one, if we were to do number one, is this line where you separate f clips g, you would just factor out the constant c, and everything else looks the same, pretty much.
A little bit. Yeah, that's worth mentioning. So you're saying here you would want to do S of CF with respect to P dot is C S of F.
Right.
Yep. You'd want to do that, but you'd also, there's another little trick here.
Right, you want that to be epsilon over c.
Yeah. And because of that, you'd want to say up here, if C equals 0, it's clear. So suppose C isn't 0. Okay, if C isn't 0, if C is 0, then you're just integrating the 0 function. And so obviously you're going to get a 0. Okay, so there's two changes to make. Otherwise, it's the proof of 1 is just simpler because you don't have to say anything about G, and then this stuff gets easier. Okay. Now, I said there's 3 results. We are to the one that I would not call a theorem. It's just a proposition. So we haven't actually integrated anything yet. We said that we could integrate constant functions. We didn't do it, but I invite you to go try it. Let's move up. Oh, Madeline points out, yes. Where I said epsilon over C. Of course, I should have written epsilon over the absolute value of C. Thank you. Okay. So now we're going to move up from constant functions, which, again, I claim it's easy to integrate, even though I didn't show you, to characteristic functions. So let's define them first. So let's say we've got a set S, and we're going to define its characteristic function. Okay. It is a function from the reals to the reals, although it's from the reals to the set 0, 1. Okay, that's a chi, not an x. My chi's aren't that great though. Okay, this is 1 if x is in the set S and 0 otherwise. Have we seen any of these before?
Yeah, we had that function way back with it was if x is rational and x is irrational.
Yes, thank you. Dirichlet's function is the characteristic function of the rationals. It was 1 if x is rational and 0 if x is irrational. Do you think that function is integrable or not integrable?
If it is, I would say that it's integral with 0.
It's good intuition. Yes, if it were integrable, its integral would be 0. But do you think it's integrable? So let's think about what would we do. We'd take a tagged partition. We'd have to take any tagged partition. Can we guarantee that this sum is going to be close to 0?
I don't think so, because any partition you make small enough, because of the density of the rationals, you're always going to have at least one rational. Well, you'll have infinitely many rational numbers, so your sum is never going to be close to 0, no matter how small you make your partition.
Right. That's perfect. So you think about expanding this out as a sum, what would you do? Oops, that's not an F. That's a chi. So Q of Ti with a delta I. And now the problem is, you have to pick these, you get to pick these tags, and the tags just have to lie in these closed intervals. And those closed intervals, one of the rules is that actually xi minus 1 is less than xi. So there is a little bit of gap in there between xi minus 1 and xi, and we know that just having a little bit of a gap means you've got infinitely many rational numbers in there and infinitely many irrational numbers in there. So no matter what partition you're given, no matter how fine that partition is, no matter how small the norm is, you can pick tags that are all rational. Okay, because they're all rational, your integral will work out to be 1. Or you can pick out tags that are all irrational. And so your integral will work out to be 0. Sorry, it's not your integral, because the function is not integrable. Your s will work out to be, you can make your s work out to be 1, or you can make it work out to be 0, or you can make it work out to be things in between. So this function is not, and I should be a little careful here, it is not Riemann integrable. Okay. As I said at the beginning of lecture, and I believe also at the previous lecture, there are other notions of integrability. In particular, there's Lebesgue integrability, and this function is Lebesgue integrable. But for the purpose of our course, it is not integrable. Okay, what I presented wasn't really a proof. It was just the idea of a proof. Yeah, Colin.
Would the same function on like the naturals, would that be integrable?
Oh, you know what I should have said? So I was being a little bit silly here. And then let me fix what I said, and then I'll answer your question. I need to restrict this to some bounded closed interval, right? The way I've written it, I'm integrating over the entire real number line, and that is not something we do in this course. Okay, so we're not doing improper integrals. We're not integrating from like minus infinity to infinity. Now, Colin asked, what if we integrated the naturals? Yes, that would be integrable. In fact, that is going to follow from our result that we're going to prove. Now, it's not literally our result we're going to prove. You're going to have to wait until we talk about the consequences of this result. But if you pick any point, S, and you pick any closed interval, AB, and you look at the characteristic function of just that one point, this is integrable. And to say it is integrable, I'm going to just say that it lies in this curly R AB. And any volunteers for what its integral should be? Try again.
0.
0. You'll notice I put the parameter of chi there. That's just kind of an option when you're writing an integral. If you think it helps things, you can put the variable there too. Okay.
Isn't this similar to the Dirac delta function?
Ah. What is the difference between this and Dirac's delta?
The domain.
No. Nope.
No? Oh.
This integrates to 0?
Yeah. This integrates to 0, and what does Dirac's delta integrate to?
1.
Yeah.
Well, isn't that because the domain is... Oh, wait. Oh, this goes to... At S, it's 1, not some
So-
infinity.
So if we were talking about the Dirac delta, what is its value at the point?
Isn't it infinite?
Yeah. So hopefully when you learn Dirac delta, that was probably differential equations. Hopefully your professor told you that the Dirac delta function is not a function at all. Okay. Dirac's delta is a distribution. Okay. So that's the difference. Our function is a function, and at the point that we're interested in, it's just 1. It's not infinite. Okay. Dirac's whatever you want to call it is not a function, and at the point you're interested in, it's infinite. I mean, I'm not saying that there's anything non-rigorous about the Dirac delta distribution. And now my internet went out. Okay, that's awkward.
You're muted, Dr. Ben.
There we go. Sorry, wow, my Wi-Fi just cut out there all of a sudden. Anyway.
It's the engineers. They're upset with you not calling it a function.
Exactly, yeah, you're right. The engineers got back at me. Okay, so let's see. I wanna get through our material today, so let's go into the proof. Okay. We may assume that the point we're interested in is in our domain, is in our integral AB, because otherwise the result is trivial. Right? Otherwise we're just integrating the 0 function, and we know we'll get 0. Okay, sorry, I'm going to go over this a little fast, just because I really want to get to the next results. So what are we going to do? We're going to let an epsilon be given. This is how we prove that an integral exists. Now, the delta, the quote-unquote delta we're going to take that defines the fineness of our tag partition is going to be epsilon over 2. But I'm not actually going to, I'm not going to let delta be epsilon over 2. I'm just going to take a tag partition with that norm, okay? So let P dot, and I'm going to name, remember the way I defined it, a tag partition is a partition together with some tags. Be any tag partition with norm less than epsilon over 2. Okay. Suppose now I'm going to give names to the parts of the partition and the tags. Suppose, and they're just going to be the names that we're used to. Right, I'm just writing. I'm just writing down what it means to be a tagged partition. I'm using exactly the notation from our definition of being a tagged partition. There you go. Okay. I'm about to scroll up. Remember, we're trying to prove this integral is 0. This is the integral of the characteristic function of the singleton set that only contains the point S. Okay. So to prove that, we want to get within epsilon of 0, and our partition has norm less than epsilon over 2. Okay. Let's see. I'm going to abbreviate this a little bit. I'm going to be posting lecture notes after this. You can look in there if you want a little more detail. Zero is a lower bound on our Riemann sum with respect to p dot. That's because you write the sum out. All the summands in the sum are at least 0. Okay.
Is that a 0 or?
Yep.
Oh,
That's a 0.
okay. Just making sure. Just making sure. Thanks.
Okay, now we write out the Riemann sum. That's what it is. Okay. Now I'm going to use an upper bound on this sum. I'm going to say, I just opened the chat, that's funny. These delta xi's, they're all less than epsilon over 2. So I'll just replace them with epsilon over 2. Okay. Now, here's the crucial part of the proof. How many of these f of ti's could possibly be equal to 1? Right? So what is, oops, I'm sorry. And I didn't want to write f there. I want to write my function. Let me fix this. My function is the characteristic function of the set S. Okay, now, how many of these could be equal to 1? Any volunteers?
Yeah, the answer in the chat.
Madeline has it. Yes. Why 2?
Both through the same point, like boundaries at exactly the value S, and when you have 2.
Yeah. So we could have 2 of the TIs be S if S is one of the places where our partition is cut, and one of the tags is on the right side of its part, and the other tag is on the left side of its part. Okay, so most 2 1s, everything else is 0, and you see we've just made this perfect. So we got less than epsilon. Okay. that's it. We show that these Riemann sums, as long as your tag partition has norm less than epsilon over 2, that Riemann sum is going to be between 0 and epsilon. And that proves that it will be 0. Sorry, that the integral exists and is 0. Okay? Let's move on to consequences of this. So you've got this characteristic function of a single point. Its integral is 0. Here, let me just zoom out on our entire, there we go. That's our result. Maybe I can fit the consequences over here on the side. What if you've got a finite set and you want to integrate it? What will you get?
Should also be 0
Yeah, it's also 0. Why?
because we can take the chi s to be this the sum of the chi elements in S, and then we can add our integrals.
Yeah,
manually.
exactly. So the characteristic function of the whole sum of the whole set S is just the sum of the characteristic functions of its members. That's because S is finite. Well, no, sorry. That's always true. But the fact that the integral then breaks apart is that we can break an integral along a finite number of sums by our first result of today.
Professor, could you repeat what you just said? You were cutting in and out.
Yeah, I'm sorry about my internet. So we express this characteristic function as a sum of a bunch of characteristic functions. And then we use the first result, which said that the integral is linear. Okay. Here's your second consequence, which is even better. If you take two integrable functions and they agree except on a finite number of points, then they have the same integral. Okay. The reason for that is if f and g agree on a finite number of points, you can write, f as g plus a finite number of scalars times characteristic functions of those points. And then you can apply the linearity of the integral, and all those characteristic functions will just integrate to 0, and you'll be left with the integral of g.
So that's saying finitely many holes in the function don't matter?
So not holes.
Okay.
Not holes. So we're never going to integrate over a singularity or over a point where the function is not defined. But
Okay.
what we're saying is that, like, if you go and you change a function from one value to another just at a few points, that's not going to change the integral. Okay. And that's sometimes handy, because sometimes you just want to, sometimes you just, you do that to just change it into a function you know the integral of. Okay, so that's characteristic functions of finite sets. they integrate to 0. We talked about characteristic function of the rationals is not integrable, not Riemann integrable. I promised 3 results. Running out of time for the third one, but let's at least state it. And we'll talk about it. Okay. If f is Riemann integrable, then f has to be bounded. Okay. So let's just define a function. What's our, our characteristic, not a characteristic, our typical function that's not bounded. Let's make it 0. Would be this function. This is not integrable from, say, 0 to 1. Okay, and the point is that, this function, 0 at the origin, but make that 1, but it's unbounded on the closed interval from 0 to 1. Okay. Are there any questions about that theorem? I think
So if we're not bounded, that basically means we can pick tags to have arbitrarily large or small values, which will make the sum big enough.
Yeah, so I've got a proof in my lecture notes, and there's also a proof in the book. This is theorem 7.1.6 in the book. So we're not going to have time to do the proof today, obviously, because class is basically over now. So I'll encourage you to look at either the book or the lecture notes. But the proof is what Daniel just said. Basically, you take any partition. Your function is unbounded on at least one part of the partition, and therefore you can tag that part of the partition so that your function is big enough that the Riemann sum is bigger than any possible integral. Okay? So that's the idea of the proof. Now let me editorialize a little bit. This is another deficiency of the Riemann integral. Okay? There are plenty of places where you would believe that so-called these improper integrals, which actually you learn to take in Calc 2. There are plenty of situations where they really should exist, but the Riemann integral can't do them. Okay, so this theorem that your function has to be bounded, this is a bad thing about the Riemann integral and suggests why you might want other notions of integrability. Okay, so let me stop there for today, and like I said, I encourage you to look at the lecture notes or the book for the proof of this theorem, and I will